Hi everyone, welcome to class today. How's everybody doing? How's the connection doing? Better yet. So I know the last time we had some technical issues. So I, I think I figured it out. It was it was a mixture of two things. One of them was we were on Wi-Fi. I mean that was no good. I plugged it into the internet now. But I think what the biggest issue was actually that I was recording locally. So normally I record locally, and when I did the first class of the day, which is 302, I didn't because I forgot. And so I was like, oh, okay, whatever. I'll download from Twitch later. But when I did your class, I was like, oh, I gotta make sure I don't forget. So I definitely started recording locally, and I think that the computer couldn't handle recording locally and streaming, and it screwed it up. So I actually think that the second thing was the reason, but the Wi-Fi could have been too. But either way, 302 had no problem, so I think we should be okay. If it does start to get choppy, let me know. What I am going to do today is, again, I'm going to download from Twitch the stream and then upload that to YouTube. So I'm not recording locally, so it's very important that if I do cut off, tell me so that I can repeat that. Uh, and yeah, uh, I guess next week I'll do an intro in Spanish or something. But yes. Um, okay. So because it did cut off last time, I do want to review some of that stuff because I was trying to watch the video myself, and I think around the 46th minute it just died. So I was like, oof. But I don't know. At least when I downloaded the Twitch stream, it died. So I don't know how far it was on in reality. So the old video was definitely helpful because it's the same topic and I do use the same notes. So they're different sometimes in examples, but the topic should be the same. And especially with this one being Fibonacci, traditionally what I use is very close. But either way, let's just make sure we're on the same page. So let's just kind of scroll up to I think just from the top real fast, okay? And just kind of work our way down quickly. And then today I really just dedicated it to doing coding examples on recursion. So if we don't get to those immediately fast, that's okay. We'll just make sure we actually get the recursion down as a concept first, and then just code more. And I believe that the assignment for recursion is almost complete. In fact, I think it's complete, but the video explaining it is not yet complete. So as soon as that gets completed within a day or so, I'll post it so that you can have as much time as possible. Because I know the template one took a while, and that was my fault on this one actually. But yeah. So, anyways, I do believe that it will be the recursion one is not like a massive assignment. It's tiny little assignments of like do this in recursion, do that in recursion. So that's good and bad. It's good because if you screw one up, you don't get like fully punished per se of like losing your grade. It's bad because I guess it's not really any bad to that. It might seem like a lot of homework because you got like 10 different problems to do, but they're all really tiny. So maybe that's bad. All right. So, anyways, recursion is again another way of doing iteration. Iteration being loops. So the downside is, like I said, that there is an overhead involved because it's functions, and that overhead does take a toll on memory, which means that there is a limit to how many of these you can do, and that limit is not as big as we might think. Because when we think computers, we think of billions and trillions and quadrillions of numbers is not a limit for a computer. With recursion, like hundreds is probably the limit. Like that's kind of worse. That's nothing, you know. Like for a simple loop, you could run a loop that runs like a million times in a second, whereas like a thousand function calls can run in less than a second. So like your recursion dies before you even get to 1 second, right? So it's not good for that kind of stuff. You don't want to go too deep into recursion. Again, I said last time, the real reason you use recursion is because it makes a problem easier to solve, and it's a good prototype. If it's something you're going to put into a production and it's going to be something that like it's going to deal with big data, you probably don't want to do that. You probably want to switch it to iteration. But you start out with recursion to again prototype the problem, solve the problem, then optimize the problem. Don't try to optimize it before you solve it. So I give an example of a loop. This is a loop. The end. But the more interestingly, this is the example of the same code but using recursion, right? We have the function call, and we have the the actual code that does something. And of course, this code, kind of like this one, is gonna supposedly run for infinity. But as I said, that's not the case with recursion, because it is going to run out of what's called stack overflow. It's going to run out of a stack space for function calls. Usually, you have a limit that you can do. Like when you run a program, there's a limit like that the compiler, whatever runs it gives you. You can increase that limit, but by default, it's a pretty small limit, like I said. But in theory, you could increase it to the size of your memory and then do a lot of recursion, but it's not there by default. And you don't have admin access in like Sally, so you know you'll know if you hit those limits pretty quickly. I then went ahead and talked about Fibonacci. What Fibonacci is, you take the last two numbers, add them together, get the next number of the sequence. So you take like 8 and 13, you get 21. Uh, the next number of this sequence that I didn't show would be the result of 59 plus 89, or sorry, 55 plus 89. What is that equal to? Um, 90 plus 54, basically, which would be 144. So that, I think, whatever 55 plus 89 is. Okay? So yeah, this is the iterative code of that. It works, but it takes some processing power to figure out. This is what the math people would have given us. If I didn't explain to you what Fibonacci is in words and whatnot, if I was a math person, I would have just told you this. I said the function of the Fibonacci is computed as taking the function of the previous number plus the function of the second previous number, add those together, and you get the next number. And you have these two base cases where if you have a function of the number 1, you get 1, 0, 0, or depending on who you ask, these two be 1 and 1, right? Some people, I don't know what the pure version of the Fibonacci is, but it doesn't matter. The point is that those two are what we know as base cases. And so when you get something like this, it takes effort to convert it into this. And so it's just nice if you can just like convert this directly into code without having to really think about it. And so that's what you do with Fibonacci is you can literally just write the code like this, and it looks really, really, really similar to what you saw earlier. In fact, I chose the same function name, f, and I chose the same variable name n. And as you can see here, I have my two cases where n is equal to 1 and n is equal to 0, returns 1 and 0. That's kind of what you see here as the two lines there, laser pointer. So these. And then for these recursive case, this means that it has to be done for any number greater than 1. So that is literally just f of n1, f of n2. So this literally looks almost identical. In fact, here, they're right next to each other. I didn't notice that. But look at that. Look how close that code looks. Like this right here is this right here is this, and this right here is this. It just looks so close. And that's no surprise. That's because as a coder, if somebody tells me like do this, I do this because like that takes at least amount of brain power to like convert something from math to actual code. And that is the power of recursion, that it saves me that time. It may not be as efficient as the loop version you saw earlier, but I sure as heck can get this done in 5 seconds. I just write the code and I'm done. Now, there are problems with the math people's version of this. There is no mention here of what happens if n is less than 0. Like, there's no mention of that. And similarly, our code doesn't have a cover for that. So technically, if I feed in a negative number to this is going to run forever and going to crash. So I can say, hey, the math people didn't tell me that, so I did what I was told to do. I'm just following my job kind of thing. And so, yeah, that's on them for not doing that. If you want to be safe, you could do some like if n is equal to -1 or less than -1, return 0 or something, or send an exception. Exception handling, which we haven't really talked about, but it's very easy to pick up. You just throw an exception. So yeah. But anyways, which is what a library would probably do. But yeah, that's why you do recursion. Like this is a good example because like it's all about making your life as a coder easier. Or even if you like make code that's not super efficient. Okay. Other than that, a big thing that I said is what the components of a recursive function are. We have 3 components. We have the base case, which in this case is numbers that we know what the answer to are. We have the recursive case, which is usually a function call to yourself. That's what this right here is, and that's what this right here is. In fact, this recursive case has 2 function calls. This is a function call, and this is a function call, right? So that's happening too. And then the third component, which I kind of threw this myself. It's called like the do something component. Like the reason you're doing this recursion, just like the reason you're doing a while loop, is because you want to do something, right? You're trying to compute a number, add things together. You're trying to achieve something, right? And I consider that to be part of the recursion. Like, don't forget to do that. Otherwise, like why you're doing this, right? Like, imagine writing a while loop and not putting anything inside the while loop. Like, are you just trying to like waste processor time so like to slow down the process? You could just use sleep command for that. But like you know, you have to do something, right? Most of the time, unless you have some super high scale thing you're doing, right? So, anyways, because we know these are the three cases, I want to look closer at the do something and the recursive case. The order that this shows up in my function is going to define what I said is tail and head recursion. And this is probably what the stuff that kind of got cut off when I was doing the lecture. So that's when I'm maybe spend a little more time on it. So to give you an example of what this meant, I created an example of saying, okay, let's go ahead and write a function that can print out the content of a list. Okay? And so I went ahead and said, okay, I'm going to write a function, recursive, of course, because that's the name of the game today. And I'm going to call that function forward. And instead of a list, I guess I did a string. Never mind. So, but a string is a list of characters in a way. You can handle it the same way. It has indexing and everything. And so I have two parameters. I have a string and I have an integer. And that's kind of like the equivalent if you were doing this with a while loop, unlike a for loop. With a while loop, you know, you would have to keep a count variable to know when to stop. You're basically going to go from here to the size of the string, which is the length of that. So this is like index 0, 1, 2, 3, 4, 5, 6, 7, 8. And so now that I have that, you know, I have my function call to that. So it started at the recursion. And what ends up happening is I have my base case, which I always want to check first. You always, always, always want to check your base case before you go to your recursive case. And well, you don't have to have the do something happen before the base case. You could have like, or sorry, you don't have to have base case happen before do something. So like you could actually do some work towards your progress before checking the base case. I encourage you when you're starting recursion to always bring the base case first. Just because you want to make sure you don't get called to do the function with invalid data like you're out of bounds or something. So that's why you see me here doing my base case check first. What's the base case in this case? Well, I'm trying to print out a list, so my base case is when I'm done printing the list, right? When I hit the last item of the list, or better yet, when I hit the next item after the last, which is nothing. That's out of bounds. So what would that be in terms of the index? Well, if I know that t dot length is the length of the string, then I know that if I hit that number, then that means that I've hit the end of the string. Or, you know, I like to play it safe when I code and do extra checks. So even though this would have been okay by saying c is equal to that, I want to play it safe. If somebody calls this with a number that's just really big, and it's obviously bigger than the string, I want to make sure it doesn't run and crash. So by putting a greater than or equal sign, I'm just protecting myself of bad input, basically. So that's why you see that. But technically, equal would have been okay, as long as there's no bad input. So anyways, you always go into coding with like the idea that the person that's going to be using your code is like, no offense, but it's like the least intelligent person in the world who's like just barely knows how to code, right? You have to think of it that way, because then you are like, okay, what could this person do to like screw the code up, right? And like if you think of it that way and you just super protect yourself, you know, it's the same concept when you're driving, right? You got to drive defensively. You drive not with the idea that everyone's going to follow the law. You drive with the idea that you're the only person that's going to be doing the right thing, right? And that way you're protected. And you know, it takes two to make an accident. So if you're there, then there's way less chance of having an accident, right? So I take that mentality into coding too, and I say, let's just make my code as safe as possible because I don't know what crazy things somebody's going to come up with and break the code and then blame me for it, which is the worst part, right? That's what ends up happening with a job, you know. They blame you for it even though somebody else is the one that really should have been more careful. So better play it safe, super safe. In my case, that's the simplest saying greater than or equal to. Okay? So anyways, moving on. That's the base case. So I obviously wanted to stop the recursion when that happens. So I put a little return there like that. And then from there, I have my do something, which is like I wanted to start printing out the string because that's the purpose of this, right? So that's why I have this cout. Okay? And then from there, after my do something, I want to move on to the next item of the string, which is my function call. That's my recursive case, which I'm feeding it the same string, but I'm feeding it one number higher on the index so that it prints the next letter. Okay? This is what's known as head recursion, or sorry, tail recursion. Tail recursion. And why is this known as tail recursion? Because the recursion is happening after the do something, okay? And that's cool because that's usually what you typically see and what's easier to do, okay? All right, so then I say, okay, cool. What if I want to print this backwards? Well, I said there's two ways to do it. There's the not so cool way, and then there's the awesome way of doing it. Let's do it the not so cool way first, which is basically the same thing I had here as before, but in this case, I am going to go ahead and uh, decrease this here instead of increasing it, so it goes one less in the indexing. And when I call the function, I want to call it with the highest number, which is the length minus 1, so that it doesn't go out of bounds, right? That works, sure, but it's not cool. The cool way of doing it is the second way, okay? The second way of doing it is all you got to do is you take the same function you have for forward, rename it to backwards, which I call backwards 2 right here. And all I got to do in comparison to what I had before is just swap these two lines. In fact, if I had it like this, that was what I had before. This is my forward function, other than renaming it to backwards. But all I did is switch my recursive case and my do something like that. And when I do that, guess what happens? It prints backwards now. That's it. And of course, this is coding smart, right? This is coding without doing the least amount of work possible. I just copy and paste the function, rename this, rename that. Make sure you do that. I am guilty of not renaming after I copy and paste a function, and then it's confused why it doesn't work, only to see that I'm calling their old function here. I'm like, oh, snap, right? But yeah, rename that, and then just literally flip these two. So now this is what's known as head recursion instead of tail recursion, because the recursive case is happening before the do something case. And why does this work? Why does it print backwards? It's kind of a little weird to think about. So we have to kind of see how the function call happens. So initially, we start out with calling it on the first element of the string, which is the word inception, so the I. So when that happens, we get the base case. Are we done with the string? Well, we're not. And then instead of printing out the I, we have a function call with looking at the next letter, which is going to be the N of inception. And so now we're in the second function call with N. And again, we're done. No, we're not. We keep going, and we get called again. So you actually go and make all of these function calls. You can think of it like a little staircase that's going deeper and deeper. Got to go deeper in the dream. Where I, N, C, all the way out to the end. In fact, past the end. In fact, with word inception, when we're looking at this N, we're still not done yet because the length of the index of that is 1 minus. So we're, if the length, this is what? 2, 4, 6, 8, 9, then this is index 0 through 8, right? So when we're looking at that 8 index, we're still technically smaller than the length. And so we don't stop there. We actually do one more recursion call. We do one more recursion call. In here, we're passing now the string and then the 9, which is technically out of bounds because there's nothing on 9. But when that recursion call happens with 9, and we run this statement, we see that 9 is actually equal to the length, so therefore it returns. So we actually go back out of that. This code never runs. Then we go back to the 8, and now that we're back with the 8 here, where C was 8, then we run the line that says cout. So we're actually couting index 8, which is the N of inception. When that function finishes, it goes back to the one from the O, from inception. That just finished. So then we run this line of code. So it's printing it backwards. It's kind of unwinding it backwards as it's coming back up through the recursion calls all the way to the I and then finishing. So it effectively prints it backwards. Pretty cool. So, both of these are valid, but the second one is like I would consider to be like an ingenious solution, right? And it turns out that when we get to linked lists next week and the week after, the only way to print a singly linked list backwards is using recursion. Of course, you can just use a double linked list and not have to use recursion, but I'm just saying these are some examples that at least are starting to show you that recursion is useful and has its place in the world per se. But again, 302 is when you really play with recursion, and it'll be like actually like quicksort and those kind of things. All right. So just to summarize, we have tail and head recursion. Tail recursion is where you do something before the recursive case. Head recursion is where you have the recursive case first, and then you do something on the way out of the recursion, which is typically where you're doing printing things backwards and whatnot. Both of them are very, very popular when you're thinking about recursion. They're used for different things. You'll understand more about that kind of stuff in 326 when they talk about languages, and they will talk about recursion and that as well. So yeah, that's pretty much what was last class, and also just recursion in general. So like I said, today's job is going to be to write a bunch of code. But before that, I want to show you something known as a recursive tree. And I used to show this and spend like a full class on it. And I wish I still did. But none of the other instructors, I think, really do this. And so it's not on the test. And so I'm like, okay, why spend time on it then? So I am going to mention it, but I'm not going to spend too long on it. I do think it's a very useful skill that should be learned. But it's just not something that I guess other people cover it. So I'd rather spend time on the stuff that is actually on your guys' test than not. So no recursive trees for you, but I'll still show you one. So this is from video 18 of last year, because I did the test because it was back when. Well, no, I don't did the test, but that's when I did it. But then I was like, oh, I spent a class on this, and like it's not gonna be in the test. So that's the last time I decided to do it. But yeah, so one of the things that's very useful to do when you're dealing with recursion, especially code that you don't write, but even code that you do write, but you're trying to figure out why it's wrong, is to draw a recursive tree. Now, trees are something you really learn in 302, but you can think of a tree as something that has multiple children. Okay? It can have one child, it can have two childs, it can have 100 childs. The degree of the tree is how many children it can have. If it only has two childs at most, we call that a binary tree, and we really, really explore this in 302. But there's any degree of trees, like ternary tree, up to basically being a graph, which is just any degree. So they're very useful when you're trying to figure out like recursion and keeping track of like all the variables and whatnot. Because right now, suppose that I tell you find out what the Fibonacci sequence is of the fourth number, right? Of course, you could do that by hand because you know how it works. But suppose you didn't know what Fibonacci was. In fact, suppose you didn't even know what this code right here did. You know it's recursive code because you have the recursion right here. But you don't know what this is. Like, it's just some code, you're trying to figure out what it does, and you're trying to figure out what the output's going to be for a given input. So if I feed it the number 4 for n here, what is the output of this code going to be? A lot of ways that you can do this, you can just literally start crunching it out, but it can be really tricky to keep track of it because the recursion is like going to keep growing and growing and growing, and it becomes very inefficient to do it that way. What's better is to remember what, if at some point Fibonacci 3 gets called and you know what the computation to that is, the next time it gets called, as long as none of these modifies the outside of the function, you don't need to like do this again. Okay? And this is actually some of the optimizations that you can do with recursion in languages like Python to turn recursive code into iterative code behind the scenes. So you code it recursively, but the Python interpreter handles it iteratively, and that's really cool. And I believe I left the link to that in one of the videos before this. In fact, I might have left it in the last video, but if not, on Canvas there's a link as well if you're interested in that stuff in Python. It's called I always forget the name of this stuff, and then look at it, I'm like, oh, it's that, and then it goes away again. Uh, yeah, no, it's not gonna come back. No, I have not programmed in Haskell, but I have. But Haskell is that functional programming? Because I have coded on Scheme. Yeah, so I have coded on Scheme, which is probably very close to Haskell, but I don't know. So yeah, compare Scheme to Haskell. Just Google that. But even though, like, oh, don't ask me to code on Scheme right now. Otherwise, like, yeah, I'll be stuck here all day. But here, let's see, Scheme versus Haskell. Lisp Scheme. Well, there's comparisons, but it's probably like saying Java and C++ because they're both functional. But functional programming is a whole different adventure. And by the way, yeah. So I kind of wondering why you bring that. Is it because it's recursion? Because yeah, with languages that are functional, everything is recursion. There's no loops in like a pure functional language. You don't even have like variables, I think. So basically, everything has to be done with recursion. So it can become pretty crazy to do that stuff. So yeah, there is a class that is taught in UNLV for functional programming. That is a 600 level course, but 6 or 7. Actually, I think it's 700. But you can take it as an elective, as a CS, like a 400 level course. You can take it as an elective as long as you know that it's a graduate level course taught by Dr. Peterson. So if you want to learn functional programming, you can take that course, and it's pretty fun. It's just it's not my cup of tea because you have to think. Yeah, when you look at the code, it's like a million different parentheses. But yeah, this stuff comes in useful there too, actually, when you're trying to figure out why your code doesn't work. But yeah, anyways, so with recursive trees, what you do is like you basically you say, okay, how do I solve fib4? Well, you know that if you look at here, that fib4 is neither of the base cases. So you actually have to figure out what fib n minus 1 and fib n minus 2 is. N is 4, so 4 minus 1 is 3, and then 4 minus 2 is 2. So you're like, okay, for me to figure out what fib4 is, I need to figure out what fib2 and fib3 is. So then you put it as a tree there. You're like, okay, for me to, this number is not here because that's spoiling the answer, I think. But just look at these two, and you build that. You build fib3 and fib2. Obviously, you don't know what the answer to these are. You have to go back in here and plug it in. Again, neither of them are base cases. So you have to figure out for fib3, you have to figure out what fib2 and fib1 are. So you put fib2 and fib1. But notice this. This fib2 is the same one as this fib2, which means that when you finally solve what fib2 is here, you can take the result of that and plug it in here and not have to do this whole adventure down here. So that's what a recursive tree does. It saves you time by remembering what it is. Remembering. I think the term I'm thinking of for Python is memorization. Let's see. Yes, that is the term. Here's the first result from Google. It's not the one that I have linked on Canvas, but I'm sure that it will give you some introduction into that. So memorization is a method used to store the result as a previous function call to speed up future calculations, which is what we're doing. Like, if we compute what fib2 is, there's no reason to compute it again if we can remember it. It's a concept of dynamic programming, which is another thing you'll learn later on, of like remembering the result to a computation so you don't keep doing the same computation over and over again, basically. So yeah. Stream manager. What? Oh, snap. Hold on. I guess I didn't copy and paste right. I have to open the stream manager because that's where the chat is. So I guess I had that saved on the. Oh gosh, what if I had something really bad in there? Like I don't know. I mean, I just turned the computer on, but like, imagine I was googling something weird and like I pasted it. So that could have been a lot worse. So yeah, but no. I literally turned on the computer to do this. So but plus, well, no, technically I was googling some stuff earlier, but nothing that would have been bad. So yeah, but yeah, that could have been bad. All right. Anyways, um, yeah. So yeah, that's memorization. That's the term I was thinking about. And so that's the idea of remembering your function calls. So that's kind of what you're doing here by hand. So like, you know, fib2, you got to figure that out. Fib2 is made up of fib1 and fib0. That you know fib2, fib1, and fib0 because those are the base cases. So that's basically 0 and 1. So what you do is you compute that, you know what that output is, and so now you know what fib2 is, which is the addition of those two together. Now that you know that the addition of those two together is that, which is 0 plus 1, which is just 1, then you basically don't have to worry about any of this because you know that this is already equal to 1. Furthermore, this fib3 is actually made up of a 2 and a 1 here, which you know what it is from down here. which is a base case, but still, you also don't need to compute that. So really here, the work you're doing is all the colors. So once per color. So one computation of that, one computation of that, and then one of these and this, but they're base cases. So you're only doing one, two, three, four computations, and then the rest you don't have to do, even though that's how many recursive calls happen for FIP4, which is 1, 2, 3, 4, 5, 6, 7, 8. 8 recursive calls. 1, 2, 3, 4, 5, 6, 7, 8. But you only really need to do about 1, 2, 3, 4. And I guess the final thing here, 5, but I don't know if you count that. So again, it's more efficient. Plus, if I told you right now, oh, okay, cool. What is the answer of FIP5? Well, FIP5 is made up of FIP4 and FIP3. And you already know what FIP4 is because you just did that. So then you're good to go there. And you also know what FIP3 is because you did that too. So you're good to go there, whatever the answers are. And so, bam, you don't have to compute this massive tree that would have otherwise been like, let me show you what that would have been. That would have literally been that whole sub thing we just did for that. And then hopefully the copy and paste looks okay. There we go. There would have been this whole thing here too, which would have been a lot of recursive calls, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, I think. I don't know if I count that already. Yeah, 13 or 14 recursive calls. It's a lot of work, especially if you were doing it on a test or something, right? But yeah, that's the process of recursion trees. If you want to see more, you can check out that video from last year. But that's all I'll say about them. Again, they're useful when you're debugging to try to figure out what an answer should be without spending like 5 hours trying to build it up all the way up from the beginning, which is what the computer's doing, by the way. Think about that. It's doing all of those recursive calls for that. And it only gets bigger if you go to FIP6 because it's this plus the same FIP4 tree again. So yeah, very scary stuff. Okay, so anyway, that's enough of me doing stuff here. So now what we're going to do for the rest of the class is just do some recursion coding. So let's put this aside. Let's bring the keyboard here because I have the laptop keyboard, but I'd rather use this mechanical that I bought before I came here. And let's switch over. This is zoomable. That, and then I'm going to. And I'm not using a BM, even though I said I would, because I feel like the BM is going to slow down the stream. So I don't want to push my luck here with this stuff. And I'm trying to make this as big as possible. There we go. I think that's good, because otherwise when we show the output, it's going to mess up. So here, let's just go one less. All right. So yeah, this is IDE 1, if you're curious. It's just an online interpreter or compiler, I guess, technically for this. If you're coding it, you can use private. Otherwise, anything you code here is public. So like, don't code your homework because then it becomes Googleable and bad things happen. So, or if you do code your homework, at least make it private. So, no, I know. No, that is one thing I do agree with you. I wish there was a dark mode for this, but I don't think there is a dark mode. There is other websites like this that do have dark mode that I remember seeing before, but I don't remember them. This one's the one that I remember because the name just stuck with me. So yeah, sad times, especially because it's actually dark here. It's probably still bright in Vegas, but here it's like nighttime. All right, so Replit, RGB. I don't know. We could try those. Oh, you guys see Google in Spanish. Look at that. Buscar con Google. Let's try. Which one should we try? Let's try. Well, I gotta use one that doesn't require me to log in, because otherwise it's gonna be like, that's the problem, right? It's the convenience of that one. See, the convenience of the ID one is that I don't have to log in. Here, we'll try online GDB. All right, that looks nice. Is this C? Oh, why is it the switch C++ though? Language C++. There we go. think it switched. Okay, it looks so could be okay. I do think it switched, but we'll see. No, I know how to change the language. I just don't know if like I have to hit save or something. Um, I don't like that massive comment. It'll take more, and then also, well, that's actually making it bigger, right? I feel like you don't need that part there. Oh, okay, cool. All right, it's still small. There we go. You don't need the debug. Actually, this might be useful in a minute. I just want to bring this back so it doesn't cut off that. I'm almost there. Hold on. I'm trying to maximize here the screen here. So you'll take a full advantage of that. Okay, cool. All right. Let's see if it's C++ though. Or I guess since we're in Mexico, I guess that would be that, right? I guess. Oh, sorry. I instantly save Control S every time. Oh, because when I want to save my code, right? So using namespace. Okay, yeah, it worked. All right, cool. So let's start out by coding that Fibonacci one really fast because I want to see. It's gonna be interesting to see how far we can push this thing before it yells at us for the Stack Overflow. So let's just make that Fibonacci sequence code. So that was a valid returning function, if I recall. Oh, well, here I can look at it. There we go. So it's just I'm just gonna code the exact same thing that I showed you. So I want to show you that I wasn't lying about this stuff. One thing that I did mention in that previous video that kind of died was that you typically have your base case be separate from like your recursive case and whatnot, but it doesn't always have to be. And in fact, sometimes you won't see it that way, and it might be confusing to figure out what the recursive case is. And I'm going to show you really fast an example of that. That's Control C muscle memory, Control S. So for example, this is the full thing, but like some people will be like, look at you like, oh, why are you doing multiple return statements in one line of code or something? Or you could just be like part of an else clause or something. So, I could reword this to say something like, well, here, I'll make it a separate function. This looks clean. Like, okay, I know what my base case is, I know what my recursive case and everything. But somebody could write this like this. If n is greater than 2, return that, else return n. Somebody could write the code like this, and they both do the exact same thing. But the problem with the second one is that I would argue that it's not as intuitive to see the base case, but the base case is hidden in here. It's just well, actually greater than 1. That's correct. Yeah, not greater than 2 or greater than or equal to 2. Excuse me. Uh, I mean, we are actually trying to do something like this for 135, like using an online interpreter for the class instead of having you code on stuff. But then code blocks came along and that sort of got uninspired to do anymore. But maybe well, you won't see that, but future generations may someday see that. But anyways, so I just warning you, it's not always obvious what the base case is. Just as a warning, okay? So, anyways, let's try to run this with 4. Also, let's call this F2 since they don't complain each other. Okay, I almost hit Control Save again. Semicolons. F was not declared. Oh, I used uppercase F. And also, I just did what I warned you guys not to do. Remember I said I'd do this? copy and paste it and forget to update the function names, it would have worked too. The code would have worked actually with the other one, but not the way I wanted it to. So yeah, be careful about that. Okay, so is the, oh, I have to scroll up. Okay, 3 3. See, so that is correct. Okay, now let's push this to the limit and see what happens. Let's go with 100. Actually, you know what? I would like to print out one more thing in here. All right, I'm gonna cheat. This is what you should never do. Don't. I mean, well, you can do whatever you want when you're coding your own code, but like if you code this in somewhere else and like they look at it, they're gonna look at you like and shake their head basically. Don't make a global variable and call it count, and then like throw that into your functions. That is now going to be able to keep track of how many times this function actually gets called. Okay, and I'll do that for that one of them. And now I can actually print it out. And let me comment out this one for now. Nope, not Python. And then see out count. All right, this is like this is what you should not do. Another way you could do that, by the way, is I could have made it a static int count equal to 0, and then say count plus plus. That should be okay because this is gonna not touch this one. But yeah, that would have worked too. This is like better, but still like, you know, people will still look at you kind of weird, but not as bad though. They'll just look at you weird versus like, judging you behind your back kind of thing for doing that. Line 3. Oh, type. Every time you see the GitHub thing come up, you have to take a shot. All right. So as you can see, we have nine calls. Is that what we had here with a recursive tree? Let's see. Did I do 54? Yeah. So we have one, two, three, four, five, six, seven, 8, and technically the original call for 4, 9. So yeah. So there you go. That's your recursive tree right there. So that seems right. Okay. I said you can do that for debugging, but be careful of doing that in actual code, like global variables and the recursion. Okay. But now let's go hardcore. Let's go to 10 and see if that runs. 177 function calls. How deep is that though? What if we wanted to know how deep the recursion goes? Because like the, oh, sorry. There we go. So I put 10 here and I ran it and I got 177. That tells me how many function calls there are, but that doesn't mean that's how deep it went. Because like how deep it went is really just this number right here, this 10. Because it would have gone from 10 to 9 to 8 to 7 to 6 to 5. So really this is only going 10 calls deep, but 10 or 9 maybe because of the base case. But there's 177 of them, okay? So for us to really hit that Stack Overflow, we have to bring this number up. 100 recursive calls. I think that'll be okay, but we'll see if it runs in time. Oh, it's taking some time now, but at least it's not crashing. I don't know what the limitations of the website is. They'll probably time you out after running code for too long. But I am actually very curious to see how far it goes. Let's bring this up. I might want to check this out. I'm actually surprised it's still running. I think other websites would have timed me out by now and been like, yeah, no, you can't do that. I'm just making this nicer while we wait. Well, it's still running, but at least it's not crashing. So I'm gonna have to probably stop it because I don't want to wait too long. But yeah, I am DDoSing the website now. But yeah, I mean, this shows you if I did this iteratively, I would have been done by now. But the problem here is that each recursion call takes time to actually like load, because I mean there's a parameter here. So you have to load that into the stack, run it, come back out, and it's also not doing that minimization stage. So like it's not efficient, you know. So that's why this is taking forever. So yeah, but I'm surprised it didn't Stack Overflow though. Although I think that I think I did install Ubuntu here, so I might get away with doing a Stack Overflow on my local machine. We'll leave this running while I do more examples. Is it not gonna like? There we go. Oh snap! Just saw a bunch of IP addresses. Whatever. All right. Yeah. Let's just Control C that, and then nano recursion.cpp. Okay. Save that. Okay. G++ rec.cpp. I know it's really tiny. Don't worry. It's just the same code I'm running. Run it. Okay. We're gonna leave it running, and we'll come back to it later. All right. Maybe it'll be done by the end of class. All right. So actually, since we're gonna leave it running, I'm gonna. Here's a nice little trick. If you want to time your code, write the word time and then run it. So when it finishes, it'll tell you the total time it took to run. Okay. So yeah, we'll leave that running. For this one, bring back my terminal code. Oh, it's because it's not running. I see. Okay. For now, I think if I can get it to crash if I just go to a big number immediately. Yeah, it finished. Oh, wait, no, no. Yeah, it did finish because it says enter to exit console. So yeah, so at least we get it to crash if we put a really big number. The reason why is because whereas in the other one it's going like this, going in and out of the recursions computing, with this one it's so big that basically it's it's going it's going what is this, a million? It's going a million recursions deep, and that's killing it. Okay? In fact, here, let's run that one locally really fast. Because this one actually gives you a better error when you run it, and I want you to show you that error, and then we'll go back to running it for whatever that was. Really, it's not gonna crash locally? Wow. Okay. I guess we go bigger. If this lags out the stream, it's gonna be very sad. Oh, it's because I didn't compile it. That's why. It's already warning me. Oh, that's just because it's a bigger int. Whatever. It's not a negative number, so I'm still okay. Segmentation fault, core dump. I thought that was gonna be more exciting than that. Do I have GDB installed? No, I don't. Okay, I don't want to install it right now. That would show me the call stack. But sometimes you get a better error saying like uh, call call stack out of memory or something, stack overflow, actual cool messages. Let me try with a smaller number again. It's just saying core dump. But anyways, as you can see, the crash, it crashes for sure. All right. Anyways, I'll bring this back to what I had, which was, well, what did I have? 1,000 or 100? We'll do 100 though. I think that'll be long enough before we finish. We're not even finished before class ends. All right, we'll leave that running. Anyways, so yeah, you can see that it running a loop a million times is not something out of the normal, right? And that it just runs, no problem. Whereas here it's like it crashes. So you can see the limitation of recursion already. So okay, that's enough of that. Let's go ahead and here I'm going to save this to a notepad file so that I can add it to the list of code later, since I don't have that list of code here. But I copied it, so now I'll erase it. What are some other fun things you can do with recursion? We already showed you how to print something with a list. Let's talk about. Let's see if I got some examples of some things here. Ah, yeah, this was good. Whether something is a palindrome or not. So what's a palindrome? A palindrome, drome or drome? Palindrome. I think palindrome was the name. A palindrome is a word like race car. It's a word that if you read it backwards, it'll be identical. So if you flip race car backwards, it literally says race car. Like ooh, mind equal blown. So like this is equal to this. Another palindrome would be like LOL, I guess. That's a palindrome too. So is any single letter word like I is a palindrome because there's only one letter. So look at it in the mirror, it's still an I, right? So what do we want to write a function that can tell us whether something is a palindrome or not? It's a little trickier to do this in the while loop actually. So I think this is a case where it might be easier to do with recursion than with a function or with a normal like loop code. So we're gonna call our function is palindrome. Seems like a fitting term. And we are going to pass to our function the string that we want to check. So we'll call this string t. And then we are going to pass it the two indices that we're comparing against each other. So, left and right. And passing by value is fine. Although I would pass this by reference because that'll be one less piece of memory that has to load between function calls. You all saw with the first assignment how passing by reference versus passing by value massive lists actually saves time. So yeah, in fact, if you want to be safe about this, since it's by reference, then you can have the word const. Oh, there you go. Okay. Um, let's just make sure this runs. Okay. All right. So let's create a string in main that we're gonna check. So let's put race car since it's the only one I can remember right now other than the LOL. And then let's put one that's not a palindrome. Racy car. Racer car. I don't know. Oh wait, that's still a palindrome. That's still a palindrome. Race bar. There we go. Okay. And then maybe we should do some edge cases like I nothing, and then maybe one palindrome that doesn't have an even amount of words. So like race or rack car. That one. Difference being that this is like even number of words, where this is odd. These are just, you always want to kind of check the edge cases. So that'll be good. Okay, so uh, let's go ahead and try to call our function. So where we're going to call it is we're going to say is palindrome. Well, we're going to see out this. So we're going to say see out, and then the letter maybe A, and then the value of S palindrome. So maybe like that. Okay, which will give us true or false, or 1 or 0. I don't know what it'll return. Probably 1 or 0. And then the parameters of the string. So let's say A. And then the left is always going to start at 0, and then the n is just going to be the length. So that would be a dot length, and that's it. Although I prefer length minus 1 because that one is valid. The index is valid. Okay. Oh, fail. All right. It's like some unit testing going on here. Okay. So how do we do this? Well, the way you want to think about it is check the first and last letter of the current string and then feed the remainder of the string to the next call. So go ahead and compare T0, or well, TL, because it's the left side, and T right, which is the right side. And if they're equal, then you are good to go, right? You're like, yes, they are fine. If they're not equal, then you know that this is not good to go. So you can stop checking at this point. So you can just go ahead and say if they're not equal. Why is it having? There you go. You can say return false. Otherwise, if they are equal, then that's when you want to say, okay, if these two are actually equal, then it's possible this is a palindrome, but we gotta check the next innermost ones. So do another recursive call and return the result of that. So you can say the left plus one and the right minus one. Okay? Now this is kind of good, but you also need to add an additional kind of base case here. And that is what happens when L and R go out of bounds, right? That's when we gotta stop. So another if statement you want to say is if the left is greater than, you know, if you really wanted to make this efficient, we make them stop when they're equal. But you could also just make them go all the way around by just checking whether L is greater than the length and right is less than 0. So let's go with that simple version first, and then let's make it more optimized. Let's calls, okay? So I'm just gonna say if L is greater than the actual length minus or equal greater than or equal to the length, then I'm gonna say stop. Basically stop, which we have to figure out we return true or false here. So if L has gone out of bounds, it means that we don't need to check anything else. So technically speaking, out of bounds is okay because everything else could have been okay. So I'm gonna go ahead and just return true for that. I gotta do the same check for the other side. So the right is going down. So if the right is less than 0, then that's also out of bounds. So I also want to stop. And I'm going to return true there too because that's not breaking any rules. Okay? So I got to check all those. I could have combined this into better code, but that's, again, we're making this as simple right now. And I think this is somewhat robust now. The only problem might be the center, but I think we'll still be okay. But here, let's just run it and see what breaks and what doesn't. Okay? So we got, oh, I like how this outputted. That was not my intention, but I thought it would add a line feed between them, but that works. Okay, so A is true, B is false, C is true, D is true, and E is true. Is that what we did? Yeah, those are actually all good because this is the only one that's not a palindrome. So yeah, we got it. We got the code working. If we want to be extra safe, let's try race. Let's try race car. Here's another test that we didn't think about with something extra after that. Let's see if that breaks it. Or no, that's just gonna compare them both and whatever. We'll still test it. We'll call this test F. And one more that I thought about is just no, that's enough. I don't think we have any other possibilities. In fact, I think that one is not really something that we need to test individually, but why not? All right. So we run that, and that is indeed false. Okay. So yeah, this works. However, it's not very efficient because if I draw you what is happening there, with race car, you start out with your left and your right. Then this moves here. This moves here. It's checking those two. Move here. Move here. Checking those two. Move here. Move here. Checking those two, which is the same one, which is okay. That's actually good for us. But then it's going there and it's checking that with that. And then it's checking that with that again. And then checking that with that again. Oh, I broke my arrow. And then after that, it goes one more out of bounds. And then it stops and returns. Right? So yeah, sure, the code works, but like we're checking something unnecessarily too many times. So we could update our base case to handle that in a more elegant way. And I think that that would be something along the lines of if L is greater than R, return true. And I think that will basically do the same thing here as all of that. I think. I think that will be good. If they're equal, you still want to check. Well, actually, no. If they're equal, you're also technically done. So we can save one more case like that. There you go. Uh, I want to add my global again to do the counts to show you that this is more efficient actually. So let's just throw that in here, and then we should have made a function for this stuff. Let's go ahead and add here. Okay, so we'll say count. Like that. I know it's off screen, but all I'm going to do for this is after I set it, I want to reset count to 0 so that it starts counting correctly for the rest of them. Okay, so let's run it with the old version first. So let's go ahead and comment out this and this, and uncomment the old version first so you can see that that's slower. Let's run it. Does F5 work? Oh, it's F9 in here. Oh, okay. You know, it's Mondays and Wednesdays is C++, Tuesdays and Thursdays is Python. That takes a while to remember. Okay, so we can see that the first one takes 8 counts. That's because it's going basically 1, 2, 1, 2, 3, 4, 5, 6, 7, and then the outside's 8, right? So it's, like that's 1, and then when it moves here, this is the second one, the third one with the C's, the fourth one's with both of the E's, the fifth one is with the backwards like that, and so on, 6, 7, 8, and eventually this is going to be the eighth one, okay? So I forgot to flip the letters there, but you get it. All right. So and then with the 3, it's basically going for every single character. Not efficient. Not efficient. Now we bring in our version 2, charge more money for it, and then you can see we are still getting, I believe, the right answer for everything. Yeah, everything except this one and the second one of the palindromes. So it's good. Look at that. Now we're only doing 4, which makes sense. We're only taking half of them because we stop when they overlap. So and then you can see that if this was not equal, then I think we would have 1 extra check. It would be 5. See that? So it's good to make that equal. Again, this is okay, but I like to play it safe and go with that. Oh, dang it. Sorry. So yeah, so I went ahead and changed it to the count, comment out the other one, the old one, run it again. And as you can see, count is down to 4 for that first one. So we are indeed saving 4 recursive calls. And it's more efficient. And of course, if we make this greater than or just equal, or sorry, just greater than, then it's not as efficient. We have 1 extra check, makes it 5. So the most ideal is to make this equal. But again, I like to play it safe and make it greater than or equal, which gives us both efficiency and safety that we screwed up something somewhere. So there you go. Another example of recursion. So I'm gonna put that down there. Okay, I saved it to the file that I'll upload later. Okay, we got 10 more minutes. Let's try to think of something else to throw in here, recursion wise, that we can do in 10 minutes. There's some fancy ones that I don't want to go over because I mean, this one's you can just code on the fly, but like there's one to convert like integers into binary, but I would have to actually think about that for a minute to do it, which I don't want to because I'm not trying to solve problems. I'm trying to just show you examples of recursion. So, what could be something nice? Well, let's do something as simple as trying to do like a power function, so like 2 to the power of something. So we'll call that pow. We don't use doubles ever, so that's a good example. And so in this case, the two numbers you typically pass to power are the numbers that you want to use. So like I don't know, the base number and the exponent. We'll do integer for the exponent. Okay. Hopefully that's not exp is not reserved word, nor is pow. We'll see. I think we're okay with that because we're not importing mad library or something. So we pass 2 to the or 5 to the second power and pass pow 5 to the third power. And suppose we were doing this with a loop. Let's do a loop and then convert it to a recursion. So we would say something like while, and let's just make it as pure as it would be with recursion. So I would just make this some infinite loop. I would add a counter, which would be my exponent basically. And then here I would say if count is less than 0 or equal to 0, break. And before that, I want to make sure that I compute by taking base and updating it to 5. The base itself, right? Yeah, exponent. Okay. So this, I know this looks weird to you, but like that's I'm trying to show you what it would look like with if you're like really blocked with recursion, you can think of iteration and then convert it. So I believe that this would work. I gotta return it. Sorry, return base and put that outside the loop. And also, again, it's not Python, so we need curly braces. Oh boy, I forgot to increase my count or decrease it actually. Okay, let's go ahead and see out the values so we can actually see them. Oh my gosh, that's not what I thought it would be. Something went really wrong there. My exponent is 2, so this should have been 2, 1, 0, and came out, but something went wrong, real wrong in here. Base times base. Why did that give me that? That's weird. Anybody see the issue? Pow 5 2. Maybe it's no. Oh, what is? I don't like how I did not tab this. That bothers me. Let's start by tabbing this out. That might show us something we're not looking at. If count is less than or equal to 0, break count minus minus. So we start with count with 2, and then it goes. Oh no! This. Oh god. Wait, is it that actually? I don't think it's this. I don't think that's causing it, but it could be. Nope. Oh, no, that's not causing it either. It could be causing it by this, but it's still a really big number for that. So like the first time this runs, base has the value of like 5. So it gets 5 times 5, which is 25. No, that is causing it. And then 25 gets to 1 and then to 0. Is 25 times 25 this number? Maybe that's what is causing the issue. Yeah, that's probably it. So the base here keeps getting updated when I don't really want it to update. I want to keep it the same. I want the answer to update. So maybe I should have put an answer here variable. 25 times 25 is 25. Okay, then I don't know. It's weird. It's doing weird things. Let's see if that someone fixes it. Nope, that just broke it complete. Oh wait, yeah, return answers here. Okay, I don't know what the code was doing. It was doing some weird things, but at least we fixed it, right? So we shall just look past that and never discuss it again. Okay, so that became unnecessarily hard, but at least now we have an iterative version. Let's make a recursive version that does not give us a headache like this. So let's call this old POW, and let's make new POW. Okay, what does that mean? Oh, it's the thing where you give it to your friend again because he can't get it. All right. So now that we made a recursion, then we can go ahead and make our lives so much easier by saying, okay, we are going to compute the next value of this. So we're going to say answer is going to get our base. And then we are going to do recursion and say the answer is going to be the current answer. We'll probably simplify this in a second. I'm just trying to process this as I type. And it's going to be the same base as before, exponent minus 1. So was it a random person that was like gifted the sub, or was it like pre-planned? I'm curious. What if it was like someone who was totally AFK? Oh, it goes to random viewer. At least they're here though. That's a test that at least they were actually active. Oh, well, active. Oh, so they must be chatting. Oh, interesting. Cool. I guess you owe him. You owe him one. Or him or her. I don't know. But yeah. Okay. So, anyways, we got to think about the base case, which is when the exponent hits 0 or less than 0. So I'm gonna go with exponent being less than or equal to 0. We can fix that if it's not the case. And for this one, I want to return. I don't want to break it, so I'm gonna return 1. I think that'll be okay. And I think all I have to do is put base here. And I can get rid of all this mess. I don't know if this is right or wrong. I think I'm just gonna run it and see if it's right. The first one's right. Wait, that looks right. So maybe the previous one was not right. No. 5 times 5 is 25 times 5 is 20. Yeah, so the other one was still messed up, I think. But you can see how easy it is to make it in recursion versus loop. Like, the loop one's just like, oh, it's all pow, not pow 2. Here, what I should do is just put it twice and then just put the pow on the old pow. Yeah. So, oh, and then of course, end lines. The semicolons don't really matter to have the extra ones. All right, so the first one's still broken, but the recursion one does not. And you can see how clean the recursion one is. Like, look at that. Like, look at that, and then like, look at that. I mean, sure, we were trying to do an infinite loop, and that is kind of the reason why this is bad and broken. But you know, it's just when you're thinking recursively, trying to make it iteratively, just like it's not. You have to think differently. So Now, so fixing this, I think maybe if we make this like a 1, maybe that'll fix it. That just kind of made it okay-ish, but not really. Mm. Yeah, I don't know. There's probably an easy fix to that, but I don't want to bother with that because the recursion one is short and nice. In fact, you want to make it even shorter, put it like that. You can say, I wrote my 2 lines of code for recursion. Recursive case, not recursive case. In fact, could I get away with 1 line? Not really, because the if statement is technically 2 lines. And I could flip this to put the if statement here, but I still need to return this one somewhere somehow. So yeah, but yeah, so that's just another example of recursion. Like I said, recursion is one of those things that I could show you a million different examples, and you're still going to be the same spot as before because you just have to do it to get comfortable with it. If you get comfortable with recursion, then you're okay. And if you don't, then you just got to do more recursion until you get comfortable with it. There's no shortcut to it. There's no algorithm like, okay, step 1 do this, step 2 do this, step 3 do this, step 4 profit. No. This is more like step 1 do something, question mark, profit. That question mark's always going to be different. So, you just you just do it. You got enough chance for extra point. So I'm thinking maybe hold off on it until we get closer to, at least until I'm back, and then you can redeem it at once. Because what I'm gonna do when I redeem it is I'm gonna have you email the TA your I was gonna do it myself, but well, I can just make the TA do it. So what you'll do is you'll send your Twitch name and your real name to the TA, and I'll send a list of everybody who redeems it to the TA, and then they'll compare them and find you and check off, make sure we have everybody's name who redeemed it, and then award you the points. But I'd rather do that in one list instead of emailing her like daily, so that she doesn't get bombarded with emails. She probably has enough with the questions. So yeah, just hold off until like maybe like we're not gonna wait till the end of the semester, but at least till like I'm back. So maybe like the 15th of November. And then we'll start. I'm also going to start offering smaller tiers there, so you can, I think that so people that are halfway can still redeem points if they want and whatnot. So, yep. Okay. Well, that's all I have for you. Like I said, recursion is just practice, so you'll get it after a while. It'll be ingrained in you. So just keep practicing recursion. I'll get that assignment out there as soon as possible so that you can actually get playing with that. But of course, you also got the template stuff to do still. So yeah, just you know, like I said, we're done with C++. These are just concepts. The next thing on the list is going to be linked list. So that'll be what we'll talk about next week. And I will do some recursive examples with linked list. Like I said, I will print the linked list backwards. So I'll try to throw as much recursion as I can for the rest of the semester. But we are going to talk about a different topic. So yeah, we're in pretty good shape right now. We're on schedule. Don't forget, test is coming up. I think it's 2 weeks from next. It's not the next week, but the week after that. I think. I'll triple check, but just be aware of that, so that way you know you're aware. And I'll tell you what. I don't know if recursion will be in it or if it's the last topic that will be in it. I'll update you on all that. But for now, have a good weekend, everyone. I'm out there if you need me or the TAs. I don't know. That's the problem. Like they're making the test, not me. But I think this one will be easier than the first one because like you learn very systematic things like operator overloading, templates, uh, virtuals maybe by tricky, but virtuals you got. But they're very systematic things that you can do a cheat sheet for. Like this is how you do especially for operator overloading or templates. Like have that cheat sheet stuff like kind of how I showed you, so that you can do that quickly and remember it. Recursion one, I don't know if that's going to be in this test. Probably that one's probably tricky because I don't know what they're going to make you do. But I wouldn't be surprised if they do the palindrome. That's such a popular question for when you want to test someone for recursion. So that's why I did it too. So yeah, we'll see. I'll let you know as soon as I see the test. I'll give you some hints if I can. But yeah, all right then. Well, if nothing else, then enjoy your weekend. You know where to find me. I might be far away, but I'm still close through the internet. So have fun, everyone. Bye. Thanks. Have a good week as well.